All right, are you guys ready for 5.2? So 5.2, pretty similar to 5.1, except for this time we're going to look at some applications of exponential decay. So it is possible that something just decays really fast rather than growing really fast. Okay, one of the biggest examples of this is decay of radioactive isotopes, and that's what we're going to look at here as we first try and figure out, okay, how does this pattern change when we have exponential decay versus exponential growth? So we're going to look at iodine 131, which happens to be a nuclear medicine used in medical tests such as thyroid function. Okay, it decays over time, so it tells us, since we know how fast that decay happens, you'd have to go to a science class to figure out exactly how this works for testing thyroid function. But anyway, we know that it decays away over time since it's this radioactive isotope. You've probably studied these in any kind of chemistry class or something like that, if you've seen this before. So what we're looking at is we're trying to find that pattern in decay. So here's we're looking at 8-day time periods. We're seeing it decay over time. So we start with 160 milligrams of this iodine 131, and it decays away 80, then 40, then 20, and 10. And if we graph each one of those 5 points over here, we see that exponential decay. This works a little bit in the opposite direction of exponential growth. It's going to decay really fast at the beginning, and then as we have less left to decay away, it kind of starts to level out. Okay, but we're visualizing exponential decay there on the graph. So what we want to do is now come up with the pattern that's happening with exponential decay, so we can put an equation, a kind of standard equation, to this exponential decay. So again, just like in exponential growth, we're trying to figure out, okay, if it's exponential, it's continuous multiplication, what are we doing to 160 to get to 80? And you probably recognize that there we're taking 160 and dividing it by 2. But now we know from exponential growth that we want to think about this more like repeated multiplication. So if we divide something by 2, that's the same thing as multiplying it times 1/2. So we want to think about 80 as taking that original quantity times 1/2 to get to 80. And then again, we want to keep working with that initial value. So we say think about 80, we're going to think about 80 as 160 times 1/2. And then again, you see we took 80 and took it times 1/2 again to get to 40. And if we take 80 times 1/2 again, that's the same thing as taking 160 times 1/2 twice. And we start to see that exponent come into play with a new kind of factor, 1/2. So we take 40, this here equals 40, right? So we take that version of 40 times 1/2 again to get to 20, and that gives us 160 times 1/2 3 times to be 20. And the final one, can you see the pattern, would be 160 times 1/2 4 times to get to 10. So we have a new pattern. It works out very similarly to exponential growth. We're still going to say, okay, if y is that amount of iodine 131, and that just happened to be in milligrams for this problem, looking at that table, and if x is our time periods again, then we see a very similar relationship as we did with exponential growth. We're going to start with that initial value each time, and we're going to multiply it times 1/2 every time, and that exponent matches how many time periods have passed. If it's 3 time periods, we multiply by 1/2 3 times. If it's 4 time periods, we multiply by 1/2 4 times. So our final equation takes those milligrams, we take the 160, we take the original amount, times that, now we're going to call it a decay factor, however many times we have a time period for each time period that passes. Okay, just like with doubling time and exponential growth, we often look at this decay in terms of this half decay or this half-life. Okay, so we have kind of a typical, just like doubling time, a half-life thought when it comes to decay, and that is just what it sounds like. It's the time it takes for half the substance or whatever we're looking at, so half the substance to decay away. Okay, and we'll often quantify that decay in terms of a half-life. So since our time periods here, if you go back up, we'll see our time periods here for iodine 131 were 8 days each. So that meant our half-life, we were quantifying this decay in terms of its half-life, which was 8 days. And we would do that a lot, especially with radioactive isotopes. We'll classify their exponential decay in terms of their half-life, rather than saying what happens in just 1 day. Okay, so exponential decay function, very similar. We still have y equals c times a to the x, but the big difference now here is that for decay, we're always going to multiply by a fraction or a number between 0 and 1 so that that original amount does decrease. As soon as a is greater than 1, we have growth. So for decay, this is the main difference now. We know that a will be between 0 and 1, and that creates the decay in exponential growth. Everything else is still the same. A is still a factor, but since it's decay, we're going to call it a decay factor rather than a growth factor. It's still the amount y is multiplied by as x increases. It's just that now y is going to get multiplied by a fraction. That original amount is going to get multiplied by a fraction with each decay. C is exactly the same thing. It's still thought of as that initial value. How much did we start with? Also, as we start to visualize exponential functions, in actually 5.4, we'll see that that is also the y-intercept, very similar to linear equations. All right, so let's use that same idea, finding a decay factor, understanding x and y, using that c as the initial value to set up some and use some equations. The first thing we're just going to do is use that exponential decay function, make sure we can work with that exponential decay function in terms of those half-lives too, before we start thinking about setting up some more equations. So I want you to use your model we just came up with to figure out how many milligrams, so that means we're looking for a y, how many milligrams would be left after 32 days. Now be careful here because x was time periods of 8 days. So when we think about using our function y equals 160 times 1/2 to the x, we have to think about how many time periods is 32 days. So you can do a little bit of unit conversion there. 32 days, we can take that times the conversion, 8 days in 1 time period so that we can plug in the correct input for x. So really we need to take 32 divided by 8, and we'll see that then for x, we need to plug in 4. 32 days is 4 8-day time periods. So be careful there, always recognize what x is in case you're given it in terms of that half-life rather than in terms of days. So we wouldn't want to plug in 32 into this particular function the way it's set up. Okay, so if you do that in your calculator, make sure you can work with that fraction. That fraction will definitely have to go in parentheses. You should get an output of 10, and that's in milligrams because our y is in milligrams. Okay, so see if you can really understand this model. Take that original model, y equals 160 times 1/2 to the x, and how would this then change if instead we started with 2,300 milligrams instead of that 160 that we originally were talking about? How would that model change, and then how could you use it to figure out how much you had left after 32 days? So for this, the only thing that changes, right, is that initial value. So we should have 2,300 instead of 160. We're still going to multiply it times 1/2 for every 8-day time period. And if we're looking at 32 days, that's still an x value of 4 time periods of 8 days. So this time we just want to take 2,300 instead of 160 times 1/2 4 times. And if we start with more, we should have more after 4 time periods. And if you again practice plugging that into your calculator, you'll see that we have 143.75 milligrams left after 32 days if we start with 2,300 milligrams. So very quickly we can change that function when we change the initial value because we know what part of the function is our initial value. Now, it seems decay is a little bit harder to understand decay factors sometimes because 1/2 is a little bit easier because you decay away a half, so you keep a half, and those two things are equal. We're going to work to find that decay factor and that C value in this next example, and we're going to see that sometimes the decay factor, we have to really think about the scenario to understand what the decay factor should be. So in this particular example, we've got a local dance marathon, and the winner is decided by eliminating a fraction, 2/3 of the dancers every hour. So since we're getting rid of a fraction, that means we're going to have to multiply a quantity times a fraction, and we're going to see exponential decay here. So we're eliminating 2/3 of the dancers every hour, and this year we have 2,187 dancers participating. We want to construct an equation modeling the total dancers left after each hour. This really starts by understanding what X and Y are. So Y is the total dancers left, not the ones that we kicked out, right? But the total dancers left on the floor. And X is in terms of hours since we're eliminating dancers every hour. Okay, so C is always a little bit easier to find if you're given it. We know we originally start with 2,187 dancers. So we know we're in exponential decay, Y equals C times A to the X. We know that C is 2,187 times A to the X. And we're looking for what A is. But we have to be careful because the fraction we're given is how many dancers we're eliminating. And we want Y to be how many dancers we have left. So if we eliminate 2/3, then we have 1/3 of our dancers remaining. So we want to know how many are left. 1/3 will be left every hour. So we need to say, okay, we need to know how many are left. So we're going to take this times 1/3 so we know how many are left, not how many were kicked out. So be very careful with that decay factor because a lot of the time we're given kind of the opposite version in our scenario. We kind of just state that a little bit differently typically in context, and we're going to use it in the equation. Okay, so we've got 1/3 for our decay factor there. So can you then tell me how long will it take for a winner to be declared? This is one of those ones where we're going to have to use some educated guessing because we are asking for you to find X, and we know if there's a winner, then the total dancers left should be 1 dancer. So we want to know, when does 1 equal 2,187 times 1/3 to the X? Again, we cannot solve for X since it's in the exponent. We don't know how to get that exponent down to a place we can solve for it right now. We have to do some educated guessing here. So you want to start by picking some values for X. Now, you can start anywhere, okay? Do you think it'll be after 5 rounds, after 10 rounds? Start somewhere. If you've gone too far, back up a little bit. If your number is too big, then up it a little bit more. So give this a shot, pause the video, test some X values, and see if you can get there. I'm going to start with an X value of 5, okay? I'll just kind of in my head always think about 5s or 10s, and my guess was that 10 might be too far because we're only keeping 1/3 every round. So this is going to go down pretty fast. We're getting rid of quite a few dancers with each round. So I'm going to keep it pretty small to start. So if I do x equals 5, I'm going to plug this into my function, then y equals 2,187 times 1/3 to the 5th. And when I plug that into my calculator, I see that I will have 9 dancers left. So I got pretty close. We're already down to 9 dancers after just 5 rounds or 5 hours. So I'm going to go to x to the 6th. I don't want to go too far away because I'm really close to 1 already, and I know this decay is going to happen fast. 2 ways you can think about the next function. You can plug it in, 2,187 times 1/3 to the 6th, or you can think about taking 9 times 1/3 to go 1 more hour. Either way, you'll get 3 dancers left. And then you'll say, okay, we're extremely close, thinking about dividing that by 3 again, or moving on to x to the 7th and plugging that into your function. You'll see that it'll take 7 rounds. Sorry, I just wrote down 7. If you take that to the 7th, you will get 1, meaning it'll take 7 rounds or 7 hours to get down to that winner, that 1 dancer left on the floor. So x equals 7 is our final answer, and the answer to this final question is that it'll take 7 hours or 7 rounds. How long will it take? 7 hours to get a winner to this dance competition if we eliminate 2/3 of the dancers every hour. Okay, so again, decay just tends to be trickier. You always want to think about what that y value is and relate that to the decay, the way that decay is being given to you in context. All right, one other thing I want to do here, so you're going to have more examples of setting up decay functions in your homework, especially with radioactive isotopes, okay, is I want to think about if we're given that half-life, that typical way to think about exponential decay, is there a way for us to get back to that original equation, that original input? So for instance, back with this first one here, when we were thinking about x in 8-day time periods, would there be a way for me to instead think about x in terms of days? So I could plug in any amount of days and not have to do this conversion of time periods. And there is, and it's actually fairly simple. We just want to understand how we get there. So we're going to do another example. Again, it's always just good to see new examples. So we're going to set this equation up just like we would normally do, but then we're going to think about how do we make the equivalent model with going down to that single unit rather than looking at, in this case, 5-hour time periods. Okay, so we're just going to start by making that original function by using time periods. So again, a good opportunity to pause and see if you can't get that first function. Let's see if you got the right thing. So in this example, we're drinking 8 ounces of coffee, and we're saying, okay, once we drink that coffee, our blood reaches a peak level of 120 milligrams of caffeine. 5 hours after the peak, our blood level is reduced to 60 milligrams of caffeine. We went from 120 to 60 in 5 hours. So we see it decayed by a half in 5 hours. So that's why we're going to work with 5-hour time periods, because 5 hours in this case is our half-life. So to construct that function, we're going to think about, okay, y is going to be milligrams of caffeine. And I again want to think about milligrams of caffeine, what? That I started with, that is left, that's decayed away. And this is going to be the milligrams of caffeine left in the bloodstream. Oops, in the bloodstream. There we go. Okay, so always think about what you're thinking, what your output variable is in that specific context. X in this case is going to be 5-hour time periods. So the amount of milligrams left starts at 120 and gets multiplied by that half-life every 5 hours. So X is 5-hour time periods, and Y is that 120 that gets multiplied by a half every time period. So this is our function if we leave it in terms of half-lives. Now, if we want to say, okay, let's make this simpler. Instead of having to convert back to time periods, what if I want this function to just tell me how much is left at any hour that I want to plug in? We're going to make that 5-hour time period just a single unit of every 1 hour. Okay, so setting up just a couple new variables. Y is still going to be milligrams of caffeine left. And X now, and actually let's just go ahead and change that variable so it makes a little bit more sense. Let's just make it T so that we know that this is different. It's just the number of hours, not 5-hour time periods. Well, think about what you would do if you were given an amount of hours. If you're given an amount of hours, every time you're given T hours, you're going to say, okay, that's in hours, and I need to convert it to time periods to plug it in for X. So X is going to equal whatever T I have times, I'm going to get rid of the hours, so there's 5 hours for every time period to convert it to time periods for X. So every time I'm going to take T and divide it by 5 to get X. So X equals T over 5 time periods. So all I'm going to do is in my function, replace X with T over 5. So my function becomes Y equals 120 times 1/2 to, instead of X, put in T over 5. Convert hours to time periods every time you're just going to take and divide it by 5, since hours, there's 5 hours in one time period. Okay, so this is a new function where now every time I can just take and plug in any number of hours, I'll just divide it by 5 in my exponent before I use the function. Okay, so let's use both models to determine how much caffeine will be left in our bloodstream after 10 hours and see if they're equivalent. So let's see how these two things work differently. So we have Y equals 120 times 1/2 to the X, where X is time periods, and we have Y equals 120 times 1/2 to the 10, oops, sorry, not to the 10, to the T over 5, where T is hours. Well, 10 hours is how many time periods? 10 hours times 1 time, oops, time period for every 5 hours. And we'll see that that's 10 divided by 5, or 2 time periods. So for this one, we're going to take Y equal to 120 times 1/2 to the 2nd power. And what happens for this one? Well, T is just the number of hours, so I can just straight plug it in. 120 times 1/2 to the 10 over 5. And you see how that math is exactly the same. We took 10 divided by 5, we're just going to do that straight in the function right here. So we get to the exact same function in just one step by taking 10 divided by 5 to get to 2. Now, one other thing I want to point out is that we're still looking at, so sorry, we can go ahead and finish this out. Both of them will be equivalent because we're going to do the exact same math for both. We're going to get 30 milligrams for each one. Because they're the exact same function, we just do the math as a conversion up here, and here we just do it straight in the exponent. But what I want to look at here is why this one is pretty powerful. So we're doing kind of the same math, just in different spots here. But what we can do with this function right here is now see that hourly decay factor. So I have 120 times, and let me just use a different color here so we can realize we're doing something else here. 120 times 1/2 to the T over 5. Now, I'm still looking at this in terms of 5-hour half-lives. If I want to know that decay factor for just 1 hour, what I can think about is breaking up this exponent. This is the same thing as 120 times 1/2 to the 1 over 5, and then to the t power. Remember that power to power, we multiply the powers, and 1/5 times t would be t over 5. So now I can think about, okay, this is just a number. What is 1/2 to the 1/5 power? It's a decay factor, so keep a lot of decimal places. Plug that into your calculator, use parentheses around both the exponent and the 1/2, and you should get about 0.87055 if you keep 5 decimals. That is 1/2 to the 1/5 power, and that will then be to the just t power. So right there we're saying, oh, the decay factor for 1 hour is 0.87. You can always think about decay factors as a percentage too. So that's about 87%. So we're saying that, oh, we're leaving 87% of the caffeine in our body every hour. Okay, so we can use this nice conversion in our exponent to also get to decay factors that mean a little bit more when we change the meaning of the exponent to be in terms of single units instead of time periods and that half-life. Okay, so make sure again that you can get this in your calculator, that you can take that 1/2 to the 1/5 power, which we can do since we can break up that exponent up here. All right, you'll get a lot of good practice with the difference between a half-life and then those hourly or whatever that single unit is, time periods, that single unit decay factor is in your homework. Just think again about breaking that exponent apart. The last thing I want to look at here is just to make sure that you really do understand the difference between growth and decay. And you're going to look at this in the 5.2 homework. So remember, the difference between growth and decay. For growth, our growth factor will be greater than 1. And for decay, our growth factor will be between 0 and 1. But there's one thing that maybe we haven't pointed out yet that we're going to run into as we do these examples. The first two are pretty straightforward. So here we see, okay, if we have y equals c times a to the x, that's the function we're comparing to, right? That's when we see a being greater than 1 is growth and a being between 0 and 1 is decay. So here we have that c is 200, we have that x just like in our equation, and a is 5. So because a equals 5 here, we have growth. And this one, we also have a pretty straightforward equation. It's just that we're seeing some different variables. Remember, this is just function notation. So our output equals 563 times 1/4 for every change of the input. That input variable is by itself. So we see here straight away that a is 1/4. That is less than 1. It's a fraction, which will cause decay. Now there will be exponential functions though that don't start with that exponent alone like we're used to seeing. This one has a negative x. We cannot say then that right now that a equals 3. That's not true because a is always what is with x alone. So we need to think about getting that x by itself. 3 to the negative x is the same thing as 3 to the negative 1 times x, which is 3 to the negative 1, then to the x. Remember, power to power, we multiply the powers. So in order to see what that a actually is, just like with the fractional exponent, we need to break apart that negative from the x being alone. This is the same thing as 1/3. Remember, negative powers move the base to the denominator. That's 1/3 to the x. So a is actually 1/3, and this is decay. So the main part I really want you to understand here is that we have to get that exponential term, that exponential variable, to be alone before we can determine decay versus growth. On this next one, we see the variable and the exponent alone. We just see a decimal for our factor. That's all right. 1.34 is still greater than 1, and so this is growth. Even if we start with a really high C value, right? It doesn't matter. That C value never comes into play. It could be in scientific notation, any of those things. We're always just focused on what is connected to that variable power. We can also start with initial amounts that are decimals. We could have less than a milligram or less than, right? An initial amount could be a decimal. It doesn't mean that there's nothing there. We're not focused on that. We're only focused on whatever is connected to that single variable. The variable is alone, so we're good there. So we can say, okay, A is 5/4. Comparing that to 1, it is greater than 1. So we're seeing growth here. Try the next two. Even though we're starting with a lot here, the A value with the variable by itself means A is 0.15. And we see here then that because that is less than 1, sorry, that was a little ugly. There we go. Because that is less than 1, we have decay. On the final one, did you notice the exponent isn't alone? We don't think about 32 when we're thinking about exponential growth versus decay. We're focused on just that exponential term. So we're thinking, okay, how can we get 4/5 to the negative x to just have a positive x on it? We break away that negative again. So that's 4/5 to the negative 1 and then to the x power. 4/5 to the negative 1, remember anything to a negative power switches locations. That becomes 5/4 to the x. 5/4 we already saw is definitely greater than 1, so this is growth. Did you get that? Hopefully so. You'll have some good examples of that in your homework as well. Okay, so that's it for exponential decay. So we understood there the difference between growth and decay, looked at some examples of how to use the idea of a decay factor and an initial value to get a decay, an exponential decay function, how to use those functions, what half-life is. All right, so hopefully that helps you understand exponential decay and gets you good practice in the homework. But if you get stuck, make sure you're either logging on to that Zoom help session on Friday or emailing me. All right, guys, hope to see you soon.